Now let's modify this equation just a bit. Here we're saying that the second derivative plus y equals 0. Now wait a minute, what's the difference between this and what we had over here? Oh, there's a minus sign. Here there's a plus sign. Do the same guesses work as in question 2? Well, let's see. If we had said y equals e to the t, we already know that y1 double prime is equal to e to the t. And if we were to check whether that's a solution, we would have to say, does the second derivative plus the original function equal 0? And, well, the second derivative is e to the t. The original function is e to the t. Do those two things add up to 0? And the answer is not really, because 2e to the t is not always equal to 0. In fact, it's never equal to 0. So these will not work. Same thing for y1 equals e to the negative t. Its second derivative will be the same, and when you add them, you just get something that's twice as large instead of something that cancels out. So that plus sign here makes all the difference for e to the t. Now, what other candidates do we think of? We already said that the function and its second derivative must somehow be related. That is, we notice that the function and its second derivative have to sum to 0. Well, that tells us that those two functions must be similar in some sense. So what other functions do we know that we can take derivatives of and still somehow retain the original function? For example, you can probably agree that if you had t squared, that wouldn't work because its second derivative is going to be 2, and 2 plus t squared is not equal to 0. So that wouldn't work. Well, how about sine and cosine? Well, if I picked y equals sine of t, now another key here is that if you rearrange this equation, it says the second derivative has to be equal to the negative of y. Now all that means it just has to have the opposite sign as y does. So it doesn't mean y has to be negative, it just means y double prime is the opposite of y. So we take a look at this one here, we see that the derivative of sine is cosine, and the derivative of cosine is negative sine of t. And we see that the relationship between these two is such that y prime is the opposite of y. So does the second derivative plus y equals 0? That's what our check is going to involve. The second derivative is negative sine t. The first function, or the original function, is sine of t. And clearly, negative sine of t plus sine of t add to 0, and 0 equals 0 is a true statement. If it works for sine, I wonder if it works for cosine. So let's also try, because we said there's going to be two solutions here. So let's also try, as a second guess, y2 equals cosine of t. Well, its first derivative is going to be sine, rather negative sine of t. And the derivative of the derivative is going to be negative cosine of t. And so once again, you see that if you add these two functions together, they are going to cancel out and give us 0. So does y2 prime plus y equals 0? Question mark. We plug them in. We have negative cosine t plus cosine t. Does that equal 0? Of course, because 0 equals 0. So we have two solutions. We have the first one being y1 equals sine of t, y2 equals cosine t. Not specifically in that order. Whether you found cosine or sine first, it doesn't make a difference. The subscript is strictly there to help us keep track of the fact that there's more than one solution. Now we're starting to get into those ones where the coefficient here changes. And if that coefficient changes, we have to adapt our guess, right? Because if you look at this relationship, this says that second derivative has to equal the opposite of 4 times y. So it worked up here because the second derivative had to just simply be the opposite sign of y, but now it has to be the negative 4 times bigger. So if one of the common things that people want to try is they want to say, well, what if I just put something out front, like y equals 2 sine of t? Well, unfortunately, that's not going to work because when you differentiate something that just has a scalar in front of it, or a constant, I should say, it stays there all the way down. So its second derivative is going to be the opposite sign, but it's not going to be, whoops, it is not going to be 4 times as large. So you can see that they're opposite signs, which the 2 would have worked up here since 2 sine of t minus 2 sine of t is 0. So one thing to note is that any constant multiple of a solution is going to work, but this 2 here is not going to allow the second derivative to be 4 times bigger. So we got to kind of think about chain rule here. If instead what I did was put that 2, let me try this, sine of 2t, and the reason I'm doing this is because I know with the chain rule, every time I take a derivative, that 2 is going to pop out. So the first derivative will be 2 cosine of 2t, and the derivative of 2 cosine 2t will be 2 times 2, rather negative 2 times 2, because the derivative of cosine is sine, and that will be sine of 2t, which is equal to negative 4 sine 2t. And now if you check, does the second derivative of y1 question mark equal negative 4 times y1 itself? Well, let's see, y1 double prime is negative 4 sine of 2t. Does that equal negative 4 times y1, which is simply sine of 2t? And clearly these are equal because negative 4 sine 2t does in fact equal negative 4 sine 2t. So we've done good. We now know that y1 is, and you can see the relationship here. If this were a 9, this would have to be a 3. If this were an 8, this would be the square root of 8. This number here has to be the square root of this coefficient because it takes 2 derivatives or 2 multipliers of 2 to build up to that 4. And another one that will probably work is y2 equals cosine 2t. For similar reasons as above here, its first derivative will be negative 2 sine of 2t. You take its derivative again, you get another multiple of 2, which is going to be negative 4 cosine of 2t. And you can see that y2 prime is in fact negative 4 times y2. So there's one solution, there's another solution, and you can see that again, we have 2 solutions to a second order equation.